So I think it's like around 4:30. I will just turn off my camera, and when Hai, you can just introduce the speaker today.
Okay, yeah, sure. So I'm glad to introduce today's speaker, Dr. Yimin Chen. He's currently a postdoctoral associate in the Department of Computer Science at Virginia Tech. And he received his PhD, I think, from Arizona State University in 2018. His PhD research focused on the security and the privacy in mobile computing. And before that, he received his BS degree from the School of Electronics Engineering and Computer Science at Peking University in 2010, and his master degree from the Department of Electrical Engineering at Chinese University of Hong Kong in 2013. His research interest, I think, includes security and privacy in machine learning and meta learning and networked security and networked systems. So and also I think he's in the job market this year. So and looking for faculty positions. So good luck for that. Yeah, I think that's a quite a brief introduction to Dr. Chen. With that, I'll turn it over to you, Dr. Chen.
Thank you for the warm introduction, Professor Sun. And good afternoon, and thank you for having me here today. My name is Ian Chen, and I'm currently a postdoc in the Department of Computer Science at Virginia Tech. Today, I'm honored to introduce our research in machine learning security and privacy from the perspective of meta learning, which is becoming an increasingly important topic in the era of artificial intelligence of things, or we call it AIoT. And these are the joint research with my colleague, Ms. Ning Wang, Ms. Yang Hu, and Dr. Wen Jinglou at Virginia Tech. So for today's talk, I will first introduce the importance of meta learning perspective in machine learning security and privacy research. Then I will share the details of two of our ongoing research projects. The first one is about defending against data poisoning attacks on distributed learning models. And the second one is about defending against privacy attacks on federated meta learning systems. I will leave some time at the end of for the Q&A, and I hope today's talk can ignite an engaging and continued conversation. So why is the meta learning perspective meaningful for our research in machine learning security and privacy? To answer this question, I would first briefly introduce what meta learning is about. We all know a machine learning model is to train to learn one specific task. For example, learn to do image classification. And in comparison, the high-level idea of meta learning is to learn from many tasks. So for example, in this figure, we show that the robot here is exposed to 100 learning tasks. And through meta learning, it learns some skills from all these tasks and becomes more confident to learn new tasks, for example, task 101. And usually the skills it obtains are common knowledge shared among the previous 100 learning tasks. This is the high-level idea of meta learning. However, today I will only focus on a very small slice of meta learning. I will focus on using meta learning as a pre-training technique for generic deep learning models. And in this figure, I illustrate the benefit of meta-learning as a pre-training method. So we can see here, the blue circle is the parameter space of our learning task. And we all know that the most common initialization methods is random initialization, right? And in this figure, random initialization is the center of the circle here. And we assume that the orange star here denotes the parameters of our task after convergence. So the machine learning training process is to move the parameters from this starting point from random initialization to the parameters at convergence. And the intuition of meta-learning is simple. Suppose we have a lot of tasks, for example, task 1 to task 100, and they are similar to our new task here. And very likely through meta-learning, we can obtain a starting point here that is closer to the point after conversion of our task. So we can see that the keywords for meta-learning as initialization method are common knowledge and also fast learning. And these two will be are very important features in our research. So now coming to part 1 of today's talk, defending against data poisoning attacks on machine learning models. First, why do we care about data poisoning attacks? In fact, they are of a big concern right now because data poisoning attacks usually cause severe damages to our society. Today, we are using machine learning models in many sectors of our society. For example, we are using them for application including medical diagnosis, autonomous driving, and also institutional intrusion detection. And data poisoning attacks are to insert corrupted samples into the training set of machine learning models and eventually harm the models. We can see from the lower figures here, a fewer poisonous samples can change the decision boundary of the victim machine learning model and cause wrong classification results on tested samples. And we all know that misclassifications in some application could directly impact people's health and wellness. And what's more, the threat of data poisoning attacks also comes from that they are very easy to launch and they are also very effective on most machine learning models. And we can see in the figure on the left here. So in the era of IoT, we rely more and more on remote nodes to collect training data. These remote nodes are usually IoT devices, and their numbers is growing rapidly over the time. And the central server here aggregates this data and conduct model training. However, such an open nature of data collection process also allows attackers to act as remote node here and then launch data poisoning attacks. For example, the central server may publish a data collection task of collecting image of digits. But the attacker can instead simply upload images of letters to launch the data poisoning attacks. And considering there are so many vulnerabilities and cyber attacks on IoT devices, defending against data poisoning attacks have practical impact to our society. The uniqueness of our approach to defending against data poisoning attack is that we try to tackle the challenge from the meta-learning perspective. So first, I would like to, so let's look at fundamentally what happens in a data poisoning attack. As illustrated in the figure here, the purple dots and the green dots represent two different classes. And the white curve is the decision boundary of the machine learning model. And in data poisoning attack, the attacker may insert a few samples with modified labels. For example, in the figure on the right here, the attacker may modify these two purple dots into green dots, and at the same time, she or he may modify the green dots, the three green dots here, to purple dots. And then training on such a data set, the decision boundary of the machine learning models is totally changed because it tries to accommodate these few poisonous samples. And this is also known as overfitting of deep learning models. So compare the left and the right figure. The machine learning model is very likely to misclassify the text sample. For example, on the left, this testing sample will be classified as the purple class. However, in the figure on the right here, it will be classified as a green class. And our intuition of using meta-initialization is that meta-learning, as we mentioned, is to extract common knowledge from the training set. And therefore, the initialization model is much less affected by the poisonous samples. And meanwhile, the initialization model also helps model training to converge faster due to the property of initialization model. And by doing so can further reduce overfitting as well. So we can see that the initialization model from meta-learning can have two properties. One is to reduce the overfitting, and one is to enable fast conversion. So based on such an intuition, we propose our framework here to defend against data poisoning attacks. And we call our approach MATNet. So as shown here, deploying our approach as the defense mechanism is very straightforward. It can be done in two steps. First, we conduct meta-learning. We conduct meta-learning on the training set, and then we can obtain a meta-initialization model file here. And we can see that the training data set here already have poisonous samples here. Then we will use the initialization model to initial our task and conduct retraining using the original training set. And from this train model, we have two output. Here we can see here. The first output is the probability vector of a text sample, which indicate the probability for different classes. And then we also have another output here. The output is the loss function of a text sample. First, we assume that the train model here we obtain is not affected by the poisonous samples, then naturally the loss function of a clean sample will be very small, while the loss value of a poisonous sample is very large. So we can simply use a threshold to differentiate a clean and poisonous sample. After proposing our defense approaches, we evaluated its performance on different applications, including image classification, document classification, intrusion detection, and malware detection. And we use the most popular data set in each domain for evaluation. And additionally, we also compare our defense mechanism against two baselines. One is a random initialization method, and the other is called DP method, which is the state of the art to defense against data poisoning attacks. And now let's see how effective our proposed attack is. Throughout this project, we will use the area under precision we call curve score, AUPR score as our evaluation metric. And we can see from the two tables here, the detection results on poisonous samples in intrusion detection domain are shown on the left table, and results in malware detection domain is in the right table. And for the different magnet model here, they correspond to the magnet model with different meta training iterations. For example, magnet 100 correspond to our model with 100 meta training iteration. And we can see that our models achieve higher AUPR scores consistently in these two domains. And if we look at the malware detection domain, actually the state-of-the-art method, the DP method, achieve a lower AUPR score than the random initialization model. And we also test our approach in the computer vision domain to see if it can detect poisonous samples from the attacker as well. And for the row here, the row here is the ratio of poisonous samples in the training set. And the results here again show that our approach outperformed the two baseline consistently. So indicate that our approach can be applied to a wide range of machine learning models. After introducing my research on security attacks in previous part, naturally, I would like to talk about privacy attacks on machine learning model as well. So in part 2, I will discuss our research to defend against membership influence attacks on federated meta-learning systems. And remember that in part 1, we mentioned one notable trend of IoT devices that in recent years, IoT devices are estimated to grow substantially, and the trend is not stopping. Actually, another secular trend of IoT devices is that their capabilities are increasingly diverse as well. And this is actually very exciting because IoT devices are used not just for data collection, but also for advanced tasks, including learning. So in other words, the next generation of IoT devices are actually expected to equip with AI or machine learning technologies. And this transcend into what we call AIoT era. So in AIoT, we envision that federated meta learning may be the more suitable learning paradigm than the traditional federated learning. And the difference between these two learning paradigms is that the goal of federated meta learning is to learn an initialization model, while federated learning is just to learn a machine learning model for one specific task. So obviously, the initialization model from federated meta learning has a much greater application potential because it can be used for many tasks as long as they are similar. And more importantly, we have two other intuitions for federated meta learning. The first one is that participants in distributed learning system do not necessarily have a lot of data to train a local model, which are meaningful for the global model in federated learning. And in comparison, federated meta learning does not have such a requirement on participants' data set. I mean, federated meta learning do not require all the participants to have a lot of training data to generate a strong local model. And the other intuition we have is that it's not wise to assume the sample distributions in all participants are almost the same, and including the data distribution at the future model consumers. So in this regard, it will make more sense that to assume that the participants' data set only shows some similarities, and we can use federated meta learning to extract this similarity and use them for model initialization. So although federated meta learning has some difference from federated learning, one common feature among these two is that these two systems will be subject to privacy attacks, such as membership inference or property inference attacks. And in our work, we focus on membership inference attack. In such attacks, the attackers use the published initialization model to infer whether a specific user or a specific samples participate the meta training process. And naturally, to defend against membership inference attacks, we will use the popular differential privacy mechanism and incorporate into the model training process of federated meta learning systems. And first, I would like to briefly introduce the training process of federated meta learning system. Specifically, we actually use one of the most popular meta learning schemes called MEMO in our system. And we call that we have a participant and central server in a federated meta learning system. And at the participant side, she or he will conduct local learning, and obtain a local model. For example, theta I here. Then she or he will upload the local gradient to the central server here, And the central server will aggregate many gradients to update the global model CERIAS here. And at the end of meta training, the central server will publish the final meta model to the model consumer. The model consumer will use the meta model CERIAS to initialize their own model and do training on top list of this meta model. So we can see that in this process, there are actually two paths that could potentially lead to privacy leakage. In the first case, for case A, the central server will publish the meta model CERIAS to the model consumers, and the model consumer can use CERIAS to infer the existence of for example, of CERIAS, the existence of one specific task. And for case B, so we can see that the participants will submit CERIAS to the central server. And actually, the central server can use CERIAS to infer the existence of a specific training sample in CERIAS. So based on these two observations, we propose to add differential privacy in these two parts, for to achieve privacy protection. So so naturally we have two privacy levels. For case A, we call it task level DP. We use this DP to prevent the model consumers from inferring membership of a certain task. And for case B, we have the dual level differential privacy, and it will not only prevent the model consumer to infer each CERIAS, and it will also prevent the central server from inferring the existence of a specific training sample contributing to each CERIAS. And corresponded to protect the privacy within CERIAS, we add differential privacy to it here in this stage. And then to protect the privacy within CERIAS, we also add differential privacy here to protect CERIAS. And after proposing our defense approaches, we evaluate its performance on several on the most popular dataset in field short learning domain. And additionally, we also compare our approach against one baseline, GBML, and this is the state of the art of differential private federated meta learning schemes in the literature. And the data sets we use for our evaluation are the first one is Omiclaw, and the second one is Cypher FS, and the third one is the mini ImageNet. Now let's see how effective our proposed approach is. Throughout this part, we will use the n-way k-short accuracy as our evaluation metric. N-way k-short denotes that the learning task for the specific machine learning model, it has n classes, and each classes has k samples. For example, 5-way one-shot means that the machine learning model has 5 classes, and in the training set, each classes has only 1 training sample. And so the same to the other NVK short setting. And here we evaluate different methods, including random initialization, non-private, and these two DPAGR and DPAGRLR are the two methods we propose for case A and case B. And also here we have the GBML. And for the random initialization, it means doing machine learning without any few short approach. And for this non-private one, it means adopting our federating meta learning system without adding any differential privacy. And we can see from this figure that when there's only a few training sample at the participants, actually we can only obtain a very low classification accuracy. And then when we adopt some few short learning method, for example, memo, then the accuracy immediately goes up to very high here. And of course, when we would like to use some privacy protection mechanism, we need to sacrifice a little bit the classification accuracy. And we can see that for case A, our accuracy will drop a little bit. And if we would like to protect more privacy, then the accuracy will also decrease further. And however, in this figure, in this table, we can see that our method can still achieve a higher accuracy than the state of the art. And for the three method with privacy protection, their privacy budgets are similar. And we also plot the accuracy curve of different model on two data set. One is the Omicron and the other is the mini ImageNet for better illustration. And we can see that of course the non-private federated meta learning achieved the highest classification accuracy on these two data sets. And still our two methods, one is the DPAGR and the other is the DPAGRLR, achieve higher accuracy than the state of the art. And within our two methods, DPAGR has a higher privacy because it only achieves the task level. It does not prevent the central server from inferring the existing of a specific sample contributing to a specific delta I. Yeah, with that, I'd like to open up for Q&A, and I'd like to thank you all for having me here today.
All right, Yimin, thank you so much. It was a nice talk. It was very related to the course that I am teaching.
Okay, really?
I'm teaching a security analytics course, which we cover in the first half of the course, the common machine learning algorithms. And in the second half of the course, basically we cover the recent attacks to the machine learning systems. Basically,
okay, that's great.
The systems that build on, that integrates machine learning, such as we cover evasion attacks.
Evasion attack.
Yes, we cover, like white box and black box attacks. Additionally, we cover some privacy issues, as you mentioned, membership inference attack, model inversion attack, and also because it's a hot topic, sometimes I cover differential privacy, and generative adversarial networks as well.
Okay.
So your research is like kind of like very related to, you know, like the course materials that I'm teaching. Okay.
Sure.
So we have some questions in the Q&A. If you click there, you will be able to see the question and
okay.
answer.
So maybe I will first read the question to the audience. I don't know if the audience can see the question, and then I will try to answer that. So yeah, and the question is from Chris Clinton, and the question is, what Ibsen are you using with differential privacy, and how are you calculating sensitivity for images? Yeah, that's a good question, and for the we are using the Ibsen delta differential privacy, and if I remember that correctly, for the Ibsen we are using the values between 10 to -4 to 10 to 10 to -5. Yeah, 10 to -4 to 10 to -5. And for the delta, I remember is between it should be less than 0.2 if I remember that correctly. And actually for the related work we are referring to, the GVML, their privacy budget is the Ibsen is 10 to the power of 10 to the power -3, and I did not remember their delta. So I mean, they are using a much larger privacy budget, but as we can see in the figure, their accuracy is not that good. And okay, and the second part is how are you calculating sensitivity for images? Actually, let me see. I will share my screen here. Yeah. So traditionally, there are three parts that we can add differential privacy into model training process. We can add differential privacy in the training samples, and then add differential privacy in the gradients, in the gradient computation. And the last position is to add differential privacy at the output. And the most the mainstream method to incorporate differential privacy is to add them into the gradients. So as you can see here, for example, for the task level DP, the GI here denotes the gradient from each node, and this part is the noise that will generate the differential privacy protection, and basically the two parameter here. For the J here is a normalization factor, and then for the C here, will be related to the sensitivity you are mentioning. So we did not care about whether the input is image or text or arbitrary input. We only look at the gradients here. So we can imagine that C should be proportional to the value of GI here, because it actually try to cover the impact of GI. Yeah, I don't know if I answered the question or not. Yeah. Let me see if there are other.
Yeah, Professor Chris Clifton actually posted some more comments to the chat.
Okay.
Yeah, for the attention to the you know, like the participants here.
Essentially.
All right, so you don't need to read that. It's
Okay.
It's just an additional comment for your information.
Thank you, Professor Kington.
Okay. All right. Are there any other questions from the participants? All right, then. Yimin, thank you so much again for your interesting talk. And I hope that we see you personally.
Yeah.
At
Sure.
Purdue sometime, you know, like probably like after the epidemic.
Yeah, actually, one of my family members went to Purdue for his PhD in information engineering department. In industry engineering, not information, in industry engineering department.
I see, industrial engineering.
Yeah.
All right. Again, thank you so much, everyone, for attending. And I will see you next week in another CERIAS seminar.
Thank you for having me here today. Take care.